Hello, welcome to the first MAT 120 video, and I am on the first page of the blue book, or not the first page, I'm on page 115 of the blue book, and we talked about this page on the Wednesday before break, but I thought it would be a good starting point to pick up here. So this page talks about comparing selection bias and confounding factors. Okay, so both those things are bad. They'll mess up your results, but they are different. Okay, they mess up your results at different points in the process. So selection bias happens when the sample, okay, is chosen from a subset of the population. So the results only reflect that subset and do not apply to the larger population. Confounding factor is different because that's where you have your two treatment groups, okay? And so you want to compare, in this example, like group 1 and group 2, and group 1 gets treatment 1 and group 2 gets treatment 2, but group 1 has all circles. Group 2 has all squares. So in the end, when you compare them, you won't know if the difference is because of treatment 1 versus treatment 2, or is the difference because in group 1 we have all circles versus group 2 we have all squares. Okay. So won't know if observed differences are due to treatment 1 versus 2 or circles versus squares. Not a fair comparison. Okay, and just one little additional note here. Small samples will lead to potentially imprecise results because there's a lot of variation, but small samples in and of themselves do not cause selection bias or confounding factors. So you may have problems interpreting results, but it's for a completely different reason. So at this point, you should pause the video and read this small excerpt from this article on page 116. Okay, so all of this came from that article. Like, I didn't bold the who was in the study. It was that way in the article. So pause here and then turn to page 116 or 117 and see if you can answer those questions. Okay, so first question here, and I don't know why it's labeled as question H. That's a typo. So first question, is this an observational study or an experiment? Okay, this is an experiment. And we can tell that it's an experiment because the participants were assigned to different treatment groups. The sample size was 320, and some examples of statistics were the 70% on pain meds before treatment versus 50% afterwards. Okay, the explanatory variable is the treatment. Okay. And the levels of that explanatory variable, there's 3. So I think the people had yoga for 12 weeks or PT for 15 weeks or like educational materials and newsletter. Okay, so 3 levels. So the response variable was the back pain, or the reduction in back pain, probably more specifically. Population of interest would be all with back pain. Parameters would be the true percentages, okay, for all with back pain if they received these treatments. Okay. So a lot of this is review from what we talked about earlier when we talked about sampling. Okay, so what are the conclusions? So I think they concluded that the both the PT and the yoga were effective, but the use of pain medication did not decline among participants in the education group. And the main reason that I put this question in here, what are the conclusions, is just so that you don't confuse them with parameters. Because a lot of times people confuse the parameters with the actual conclusions. Okay, so now I'm on page 118 of the Blue Book, which this says read on your own, because this is actually a review of the previous pages, but it's been a while, so we'll quickly go through these points here. Okay, so how are experiments and observational studies the same? Okay, so both have a population of interest, okay, and both involve getting a sample from a population and estimating population parameters with statistics. Okay, all experiments have both an explanatory variable and a response variable, okay, and almost all observational studies have both explanatory and a response. So that's not the key thing that distinguishes the two. Okay, so that can happen in either one. Okay, so how are they different? Okay, the main difference is with the application of treatments or lack thereof. Okay, so with experiments, this involves a treatment that's applied by the researcher. There's some interaction between the researchers and the subjects. With observational study, there's no treatment applied. Okay, so there's no interaction between the researchers and the participants. Okay, a little note I stuck in here because I didn't really know where else to put it. Explanatory variables with experiments are called factors. Okay, we don't generally use that term with observational studies. Okay, with experiments, the comparisons are made between the treatment groups, and it's very important that all treatment groups are the same except for the treatment. Otherwise, just like we saw on a previous page, like if you got circles in one, squares in the other, you can't tell if that difference is because of the treatment. Now, with observational study, like usually there are comparison groups, okay, but they're not technically what we refer to in statistics as treatment groups because there's no treatment applied. The researchers just have to take what they can get basically. Okay, so and this involves where the big difference is this whole idea of whether or not treatments are applied, because with experiments, confounding factors can be eliminated if the treatment groups are randomly assigned. So random assignment, very, very important. Okay. Whereas observational studies, since there's no interaction between the researchers and the subjects, there's not the same potential for eliminating confounding variables because there's no treatment being applied. Okay, now moving on to page 119. Refresh our memories with some definitions here. Recall that a treatment is a specific experimental condition. Okay, that will become important here in just a minute. And while we're doing definitions, an experimental unit is the unit to which a treatment is applied. And all the examples that we've talked about thus far, our experimental unit is a person. Okay. For example, a person. Like in the last example, we talked about the people with back pain were getting the various treatments. The experimental unit was a person. Okay, now each treatment must be applied to at least 2 experimental units so that the variation can be estimated. So for example, if you were testing pig diets and you had 3 different pig diets and you had 3 different pigs, and so for a whole year you fed, pig 1 got diet A and pig 2 got diet B and pig 3 got diet C. At the end of the year, pig 3, his name was Boris, he was just a huge pig. You would never know, was Boris a huge pig because he was just destined to be a huge pig? Or was he a huge pig because he ate diet C? If there's only one factor, explanatory variable, in other words, okay, the treatments are the levels of the factor, i.e. the possible values of the explanatory variable, like what I was just mentioning, like if they have 3 pig diets, okay, then the treatments would be like diet A, diet B, and diet C. So another example here, suppose you're testing the effect of 3 levels of noise, quiet, soft, and loud, on the time it takes for mice to complete a maze and get a reward. Okay, so what is the factor? Okay, the factor would be the level of noise. Okay. And really I should say the sound level of noise. Okay. And the levels are quiet, soft, and loud. So again, 3 levels. Okay, very simple example. 3 levels, meaning that there are 3 treatments because there's 3 experimental conditions. Okay, and then this part right here really should have been on the next page. Okay, when there's more than one factor, the treatments are the combinations of the levels. Okay, so now I am on page 120 and looking at this example. Now suppose instead of just looking at noise, we were looking at noise in combination with a level of light. Okay, so what are the factors? Okay, so there's 2 factors. And the 2 factors are noise and light. Okay, noise, like we said before, has 3 levels: quiet, soft, and loud. And light has 2 levels. Whoops. So light has 2 levels: dim and bright. Okay, so 3 levels. Oops. And 2 levels. Okay, so how many treatments are there? Okay, so to answer that question, we ask ourselves, how many possible experimental conditions? Okay, so one possible experimental condition would be quiet noise with dim light. Or a second possible condition would be quiet but with bright light. Okay, likewise we have soft with dim light, soft with bright, loud with dim, and 6 with bright. Okay? So 6 experimental conditions. Means that there are 6 treatments. Okay, and so we can list them like we just did to see how many there are, or we can look at like how many combinations do we have if we have 3 levels of one and 2 levels of the other. So we can find the number of combinations, okay, by multiplying the numbers of levels. Okay, so we had 3 on noise times 2 on light equals 6 possible combinations or 6 treatments. Okay, what you don't want to do is say, well, there's 3 levels on one plus 2 levels on the other, and so we have 5 levels altogether. Okay, so no, we don't want to do that. Okay, so now I'm on page 121, and at the top it says the experimental unit is the unit to which one treatment is applied. When the experimental units are people, they are usually called subjects. So that's actually a repeat of a definition from an earlier page. Now, to determine what the experimental unit is, you need to ask the question. When the treatments are randomly assigned to something, what is the something that they are randomly assigned to? For example, in the previous example, the treatments were randomly assigned to the mice. Okay? Okay. Now, the number of replicates per treatment is a statistical term, and that means the number of experimental units receiving each treatment. Okay, so for example, that would be okay, suppose you're testing 4 levels of noise and 3 levels of light. So again, two factors. Noise and light. And how many treatments are there? Okay, so now there's 4 levels of noise that we're going to combine with 3 levels of light for a total of 12 combinations. Okay, i.e. 12 treatments. Okay, if you wanted to have 15 replicates per treatment, how many mice would you need? Okay, so if you have 12 treatments times 15 mice per treatment, you're going to need a total of 180 mice. So at this point you should stop the video and go to pages and work on ICE 13 and 14 on pages 37 to 39 in the Orange Book. So if this video stops abruptly, look for us to go over those in the next video. But I'm going to try to add them on right here. Okay, so I'm back and I'm just now realizing that there's an awful lot of examples about back pain in this section. Anyways, this is an older one than the other one that we just looked at. And this is, again, an example of an experiment. The population would be all chronic back pain sufferers. The explanatory variable would be the conventional care versus the biweekly exercise classes. And the response is the pain and mobility. Okay, now suppose they had assigned all women to the exercise group and all men to the conventional care group, which would be obviously a really horrible way to design an experiment. But if they had done this, this would be like having squares in one group and circles in the other group. And so this would be a confounding factor. Okay, you would never know if the differences were because there was differences in gender in terms of their back pain, or if the difference was due to the actual biweekly classes versus conventional care. Which of below could cause a selection bias in the study's results, where while all participants lived in England. Now, notice that even though that might be a selection bias in terms of like extrapolating it to our larger population of all chronic back pain sufferers, the comparison that's going to be made between conventional care versus the biweekly classes, comparison is still valid. Because you want both groups to be as similar as possible, except for the conventional care versus 8 biweekly exercise classes. Okay, and here on the next page, we have an example of an experiment. Suppose you wanted to test the durability of Ziploc sandwich bags for 3 different brands with hot and cold contents. Assume you will use 15 replicates per treatment. Okay, the factors here are brands and hot versus cold contents. So brand and temperature. Okay, how many levels does each factor have? It says there's going to be 3 brands and 2 levels of temperature. So that's going to give us 3 times 2 combinations, or 6 total treatments. Okay, response variable, what's going to be measured is the durability. Okay. An experimental unit is, in this case, a baggie, or a sandwich bag, I should probably say, but I already started to write baggie. Okay. So a baggie. Is there a control group? Okay. So in this case, yeah, there's no control group because, baggies are inanimate objects. They don't know if they received the treatment or not. So how many total experimental units will you need, or how many baggies would you need for your experiment? Well, if you want 15 baggies per treatment, okay, and you have 6 treatments times 15 baggies per treatment, That is going to equal a total of 90 baggies. So this experiment is actually an experiment that was done by a former student a long time ago when I taught in an engineering class at NCSU. And we were very surprised to see the results because we both expected that the cold contents would be more durable. What the student did is he actually dropped them from the top of his shower until they broke, and that was his measure of durability. And much to our surprise, it turned out that the hot contents were more durable, and presumably, once we saw that, it seemed to make sense that when they had the warm contents, that made the bag more malleable. Okay, so going on to number 2. This one's, again, inanimate objects, because we're going to test the effect of gasoline additives. None, A, B, or C. So notice that we have 4 levels of that, which we'll need that later. Okay, and gasoline, okay, regular, super, and premium. Okay, so 3 levels here. Okay, on miles per gallon, and that's our response. Okay, and your budget will allow for 120 tankfuls. So the factors are additive and gas type. Okay, as we just said, 3 levels of gas type and 4 levels of additive. How many treatments are there? That's going to give us 4 times 3 combinations for 12 total treatments. The response variable is miles per gallon. An experimental unit. Okay, so now this is a little tricky. You know, we've had people, we've had mice, we've had baggies, and in this time, it's actually a tank full of gas. Okay, so assuming that you're going to add the additive, per tank full. So that's what the treatment is being assigned to. So experimental unit is tank full. Is there a control group? Well, there's a control on additive. But not a control on, because you can have an absence of additive, so we can have one that has no additive, okay, but we have to use regular super or premium gas. How many replicates per treatment will you have? If you have 120 tankfuls of gas that your budget can afford, okay, so apparently you do have a very large budget. Okay, 120 tankfuls of gas divided by 12 types of treatments is going to equal 10 tankfuls per treatment. Okay, and the last one we have factors. We have three different. Okay, so we have 3 different cooking oils and 3 different temperatures. Okay, so those are the factors. Okay, each has 3 levels. So the number of treatments can be 3 times 3 equals 9. The response variable is the amount of fat absorbed. Okay, and an experimental unit. Okay, here's where it gets a little tricky. Okay, it'd be tempting to think about this in terms of the number of donuts. Okay, but the donuts are going to actually be cooked in batches of 24 donuts. Okay, so a treatment is applied to a batch of donuts. Okay, we're not cooking each donut individually and then randomly assigning a treatment to that individual donut. The batches of 24 are the treatment is being assigned to. So an experimental unit is a batch. Okay, and is there a control group? Okay, so no control group. Control groups only really make sense when. Okay, so total experimental units you will need is, we want 8 replicates per treatment. We have 9 treatments times 8 batches per treatment. Means we're going to need a total of 72 batches of donuts. Which is going to be a lot of donuts.